Thank you. Is this working? Thank you to Mikhail for all the organization. It's wonderful to be here in this fabulous city of St. Petersburg. Okay, let me begin. I hope not to delay the banquet for too long. In case you're in any doubt yet, it is the 150th anniversary and it is the year of the periodic table as proclaimed by UNESCO, by IUPAC, and by many other organizations. Here is a map of just some of the events, some of the officially IUPAC ratified events, including, of course, this one, that have taken place pretty much all over the world. I just came from Malta, which is right there, where they had an event. Needless to say, and I'm sure that the audience here realizes this very well, the periodic table can be described as the ultimate infographic, a way of representing information of all kinds. It has also become a meme. This is a word invented, I think, by Dawkins not long ago, by analogy to a gene. It's something that self-replicates and spreads through culture and responds to selective pressures even. Artists have glommed onto the periodic table. Here's an example. In fact, this artist has many paintings based on the periodic table. This is one of my favorites, and I believe Peter Atkins shares my liking. I knew he does. This is from Brazil, the periodic table of soccer players. Another of my favorites is the periodic table of guitar players. These days you can find a periodic table of almost anything. Here is, I think, everybody's favorite, the periodic table of desserts. If we restrict ourselves just to real periodic tables or periodic tables of chemical elements, there have literally been more than 1,000 that have been published, either in print form or in the internet. Some of the really large periodic tables include this one at the University of Murcia, and there's now, I believe, one in the University of Warsaw. One of the universities of Warsaw has this giant periodic table. How should chemists and how should chemical educators respond to all this attention that the periodic table is getting? I have a couple of suggestions. Of course, we should embrace this publicity and this attention to the periodic table. Chemistry has enough of a bad reputation. We need all the help we can get. It's nice to see that popular books on the periodic table are beginning to perhaps catch up with popular books on physics and on biology. On a more philosophical note, the periodic table, I think it is agreed by almost everyone, represents the paradigm, the central ordering principle for chemistry. It used to be said that physics and biology have big ideas, but that chemistry doesn't have big ideas, and this is why there was, until relatively recently, no philosophy of chemistry. Well, I've suggested that chemistry has at least two big ideas. The periodic table is one of them. The other is chemical bonding, and of course they're deeply connected. I'm pleased to say that there is now something of a philosophy of chemistry, and there have been many books and publications on the subject. On the chemical education front, I would suggest that we can maximize the usefulness of the periodic table in the following way. And this is very obvious, but I think it bears repeating. The periodic table was discovered, of course, in the context of reactions of elements. These days in chemical education, we tend to put the cart before the horse, and we teach atomic structure and electronic configurations first. And so one common statement that's made is that a student might know the configuration of the element chlorine, but doesn't have the slightest idea of what the element is like. And this is not a great situation. So my suggestion is to put the periodic table even more in the center of chemical education than it is. Of course, it exists in chemical education. but sometimes it's used just to look up an atomic weight, and it's at the back of the book, and of course I'm biased because I work on the periodic table, but I do think that it could take a more central role in chemical education. All right, so what is chemical periodicity? I'm sure you all know, but it's still worth going through this extremely simple idea. The elements are aligned according to originally atomic weight, these days atomic number, and as we walk through the element line, every now and then we get an approximate repetition, as was stressed this morning, in chemical properties. So if you take a pair of scissors and you cut here, and you cut, I have a pair of scissors here, and you cut like this, and you cut like that, and then you paste these pieces one underneath the other, you get the beginnings of the two-dimensional as opposed to the one-dimensional ordering. So here's the beginning. I wouldn't want to put iron there for the obvious reason that iron is not a noble gas. How did the originators of the periodic table cope with the situation? How did Mendeleev cope with the situation? Well, he coped with the situation by, in a sense, throwing iron and some following elements out of the periodic system. He put them in this mixed bag, this group 8, where I suppose he violated the principle of one element in one place. Now, if you do that, chemical periodicity is restored, because actually, it's interesting, copper he put in twice. He couldn't make up his mind about copper. But then zinc, then a couple of unknown elements. So this is the simple periodicity of 8. The original periodic tables consisted of simple periodicity, where it looked like the period length was all the same, namely 8. Of course, we've now realized that you can get a better chemical periodicity, or reflect chemical periodicity more carefully, by going to an 18-column table. And more recently, there's been a tendency to make a similar kind of move in putting this into the main body of the periodic table. Just like the move from there to there involves putting these elements along with some others in the center, we now can move to an 18-column, a 32-column periodic table. Let me take you on a brief historical tour of the periodic table, starting with the Manchester school teacher, John Dalton. Of course, I could have started earlier with Lavoisier or even further back, but here's an arbitrary starting point. He published the first set of atomic weights, in which he set about comparing the weights of atoms. It was he who proposed that different atoms of different elements had different weights. Two, we could say, philosophical ideas that contributed to the establishment of the periodic system. This is well before the periodic system. These two ideas, the ideas of triads, the ideas of Prout's hypothesis. In about 1827, the German chemist Dobereiner noticed that you have groups of 3 elements whereby one of the elements is the average of the other 2. In 2 respects. It's the average in having the average atomic weight. What I mean is if you add this to this and divide by 2, you get this, approximately. And it has intermediate chemical reactivity. So this begins to suggest some deep mathematical or arithmetic relationship, not only underlying the elements, but underlying the relationship between different elements. It's, if you like, this is the first hint of chemical periodicity. We could say this is the discovery of chemical periodicity. He discovered other triads, you see them here. And of course, it's approximate because, for instance, bromine, this is the real weight of bromine, and this is the mean that you obtain by adding this to this and dividing by 2. Now, there was a decline in interest in triads because they're not exact and because some people suspected that this was mere numerology. Going back to his triads, when it was discovered that atomic number is the ordering principle, not atomic weight, now let's do it with atomic number, and you find a surprising thing perhaps. Now it becomes exact. For instance, this plus this divided by 2 gives you exactly 35. And of course it has to be exact because we're now dealing with an integral number, namely number of protons. So there's a sense in which triads were useful, suggestive. They suggested experiments. Some people were trying to refute the idea of triads. Other people were defending the idea of triads. Initially, the idea was in fact refuted, but now it seems to have come back. Here are the triads, or many of the triads being shown. You notice something slightly odd here, that in the majority of the periodic table, I could even have extended it here, but we haven't discovered those elements yet. In order to have a successful triads, you have to have the second and third element in the triad must be in periods of equal length. So for instance, this triad occurs because from here to here requires 18 elements, and then from here to here requires another 18 elements. So of course a triad has a perfectly natural explanation. There's no mystery, right? That middle element lies halfway between, and it's a consequence of the repeating periods. However, if you do look on this side, that's not the case. In order to get a triad here, the first and second member must be in periods of equal length. That's a strange situation. Why is that? Well, we can take care of that by moving to a table which is gaining more and more prominence called the left step periodic table, which consists of taking the S block, putting it here, and now every triad that is a true triad consists of elements in which the second and third element are members of periods of equal length. So this is actually a form of support for this adjusted table, this alternative periodic table. The second philosophical idea, as I'm calling it, is Proud's hypothesis. Proud was a medical doctor working in London, looked at a set of atomic weights that existed at the time, noticed something quite obvious. Most, or many of the elements have weights that seem to be a whole number multiple of the weight of hydrogen. So he made the obvious suggestion, all the elements were literally composites of hydrogen. Proud's hypothesis. Once again, a little bit like triads, the initial reaction was, well, there are too many exceptions. In fact, the people who refuted Proud's hypothesis were first Berzelius, who measured atomic weights very accurately, and then in Belgium, Stas measured atomic weights even more accurately. And it seemed quite clear that Proud's hypothesis didn't work. Now, to quote a philosopher of science, Karl Popper, it's not so much whether the idea is right or wrong, it's whether the idea is refutable. This idea was certainly refutable, and it appeared as if it had been refuted. And this idea seems to make something of a comeback. Now, the idea of a theoretical comeback comes from another philosopher of science, Imre Lakatos, who was a disciple of Popper for a while until he argued with him and he set up his own view of things. Of course, all atoms are composites of hydrogen in the sense of protons. Astrophysically, as we heard this morning, the atoms are literally made from hydrogen combining together. Two hydrogens form helium, and in principle, at least, two heliums combine to form beryllium. So both of these have made something of a comeback. Interestingly, Mendeleev claimed that he disliked both of those ideas. He didn't like the idea of Proud's hypothesis because he was against anything that suggested the unity of all matter, as Proud's hypothesis does. He was very much against mysticism and spiritualism. He campaigned against spiritualism. He also claimed he disliked triads, and yet, when he set about trying to predict the atomic weight of a certain element, he published this diagram, for example. If you want to predict the weight of selenium, which was known at the time, you would predict it by saying, take the weight of this, plus this, plus this, plus that, and divide by 4. And you can see it's quite successful, because the actual weight is, I believe it's 78. I didn't put it on there. It shows the accuracy of this technique. So what's he doing here? He's using triads with a vengeance. He's using triads this way and this way. And yet he claims he doesn't like triads. Now, at the risk of criticizing Mendeleev in his own country and of getting deported, Let me also mention that Mendeleev rejected atomic theory. He didn't believe in the literal existence of atoms. He rejected valency theory, at least initially. He rejected the electron when it was first discovered because it suggested that the atoms were breaking up. He was very much in favor of integral atoms existing distinctly from each other. He did not like radioactivity. He visited the Curies in Paris and he walked away saying, I don't believe it, because again, it suggested atoms were breaking up. He did not initially believe in the existence of noble gases because they didn't seem to react. Famously, didn't believe in the ionic hypothesis. It cost him the Nobel Prize because Arrhenius was on the committee and made sure that he did not get the Nobel Prize. Altogether, rather scientifically conservative. And yet, on the question of the periodic table, he stuck to it and he developed it to an extent far greater than anyone else. Continuing or picking up the historical trajectory, of course, a very influential development was the Karlsruhe Conference, in which the Italian or Sicilian chemist Cannizzaro published a set of accurate atomic weights. And this opened the door for, and again, at the risk of being controversial in this setting, this opened the door for a simultaneous discovery, which I mean almost simultaneous, I don't mean literally at the same time, over a period of a few years. And I've argued this in a recent book, which I summarize in 3 short sentences. Simultaneous discoveries are real. And I argue for the importance of minor contributors, and I argue that there are really no scientific revolutions, contrary to Thomas Kuhn's famous thesis. And this presents, the discovery of the periodic system presents a good example of this, I believe. And I'm not the only one to have argued this. The first distinct discovery of chemical periodicity came from France. It came from Émile Bégayer de Champcourtois. Here are different versions of his telluric screw, where you align the elements around a cylinder, and then if you look in vertical columns, you can begin to see some of the familiar groupings. This is slightly wrong, but there it is. This is 7 years before Mendeleev. In London, John Newlands published this very reasonable periodic table in which we see many of the familiar groupings, lithium, sodium, potassium, rubidium, and so on. This guy was born in Denmark and emigrated to the United States, and he published this rather attractive bicycle wheel with spokes. And here again we see many of the familiar groupings: nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, selenium, tellurium, and so on. Most of what we have in the Mendeleev table is already present there. Another example, Odling, also working in London, has a perfectly respectable periodic table. Some of these guys also performed the famous pair reversal. You notice here, tellurium and iodine have been reversed in order of atomic weights so that the chemistry works correctly. Lothar, perhaps the closest competitor, he had a long controversy with Mendeleev. Lothar is perhaps the first one to hint at the existence of more than 8, maybe, it looks like he's got 16 groups here. The noble gases were not known, so he was only 1 short of there being 18 groups. And now Mendeleev, the final of the 6 discoverers. But of course, as the story goes, Mendeleev gets the credit because he made predictions, and the predictions came true. It's not enough to just make the predictions. And here I've highlighted the 3 famous predictions that did come true in a matter of 15 years. There was a 4th one, the one that became technetium. Here it is. He predicts an atomic weight of 100. And this one was synthesized in 1937 in Berkeley, California, discovered in Sicily by Scerri, as somebody mentioned this morning. However, even this is a little controversial because philosophers of science like to debate the question about the relative virtue or importance of prediction versus accommodation or retrodiction. Which counts more in the discovery of a scientific theory? The popular view is that prediction, successful prediction, is all important because it has psychological impact. Because if a scientist can predict something and it comes out right, then it looks like the scientist knows the secrets of nature. Whereas accommodation means explaining something we already know. That's not so dramatic. And that looks like maybe the scientist has cheated a little bit in order to arrive at the known result. Now, however, historians and philosophers of science take maybe the deeper view and have debated this for quite some time. Let me give you an example from a different field. This is general theory of relativity. There were two important tests for the general theory of relativity. One was a genuine prediction, this one here. Einstein predicted that if a beam goes past a massive body, a beam of light, it will be slightly deflected. He predicted how much deflection. And Eddington, he predicted 1.75 seconds of arc. Eddington, a few years later, measured this deflection during a total eclipse and found this. And Einstein became famous almost overnight. There were articles in the Times of London, the New York Times. However, there was also an accommodation or a retrodiction made by Einstein, which was that it had been known for quite some time, I believe it was something like 150 or 200 years, that in the course of its orbit around the Sun, the perihelion of Mercury precesses or moves in the sky. Some of this could be accounted for by Newton's theory, but not all of it. There was a gap. As much as 40, or as little as 43 seconds of arc per century could not be explained by Newton's theory. Einstein was able to explain this to the tune of 42.9. Okay? Now this is a retrodiction. This data was known for 200 years. Should this be taken more seriously than this? And the historians who have looked into it, at least some of them, have concluded that this is just as important, if not more important. For one thing, the data was quite stable. Because it had existed for 200 years, people had measured it and measured it and measured it. This was just Einstein trying to prove his friend Einstein correct. So, it depends. Coming back to Mendeleev, he made these three successful predictions. This one, he of course, hadn't been discovered yet. The reason why I believe that Mendeleev deserves more credit than any of the others is not simply for having made predictions. It's because of something that Elena mentioned, actually, this distinction between element in the sense of simple body, or the element that you can put in a jar, or phosphorus that you can burn, or, as opposed to element as an abstract concept. Element as the thing that exists when the element forms compounds. For instance, when we think of sodium chloride, where is the sodium in sodium chloride? It certainly doesn't look like there's any sodium in there. Or the chlorine. Chlorine seems to have disappeared, and yet it's present. They're both present. How are they present? Here's a quotation from Mendeleev himself. Forgive me if I read through this. It is useful in this, and this is the very beginning of his book. Before he even gets into anything else, he considers this important. It is useful to make a clear distinction between the conception of an element as a separate homogeneous substance and as a material but invisible part of a compound. Mercury oxide does not contain two simple bodies, a gas and a metal, but two elements, mercury and oxygen, which when free are a gas and a metal. Neither mercury as a metal nor oxygen as a gas is contained in mercury oxide. It only contains the substance of the elements. Just the steam only contains the substance of ice, but not ice itself. This has been a big topic in the philosophy of chemistry, and the distinction then between element and simple body. Now in the English language, element means both, which causes a lot of confusion. Simple body, on the other hand, is when we have allotropes, for example, we're referring to the element as a simple body. what underlies that is the element, let's say phosphorus. Right? There's one element, but there's many simple body versions of it. And as I said, I propose that this is where Mendeleev was ahead of his competitors. It allowed him to go beyond the visible evidence, the tangible evidence, the measurable evidence. It gave him a more philosophical view of elements and the periodic system than some of his competitors, who were restricted to what was at hand, what was visible, what was measurable. He used this thinking in, for instance, correcting the atomic weights of several elements, as he did. He did this for beryllium, for example. He did it for uranium, and there are many other examples. Of course, none of his, or very few of his competitors went as far as this. And just as an advertisement, there's a book coming out very soon, which I have edited with Elena, on this very question. We have 14 or 15 contributions from philosophers of chemistry. Going back to the historical trajectory, around the turn of the 20th century, a discovery occurred that, for a while at least, seemed to threaten the existence of the periodic table. This is the discovery of the element Argon in 1894. The reason why it threatened the periodic system, there are many reasons. It had an atomic weight of 40, which appeared to have therefore no place in the periodic table. I'll show you why. Because there already is an element, or was an element, with atomic weight 40, namely calcium. It presented something of a novelty because it wasn't clear initially whether it was monoatomic or diatomic. All previous gases had been diatomic. And last but not least, it was completely unreactive, which caused some people to think it didn't even belong in the periodic table. That was a special meeting of the Royal Society in London. No resolution was reached. Then things got even worse, because these two discovered helium, neon, krypton, and xenon. Now you had a real problem. What to do with all these elements? Is this the end of the periodic table? Of course it was not the end of the periodic table. Ramsay himself, one of the discoverers, solved the problem because he realized that you could simply add a new column on the right-hand edge of the periodic table. Mendeleev was delighted because it showed that his periodic system could accommodate this new discovery. Now, the common story is that, of course, Mendeleev did not predict the noble gases. The usual story is nobody predicted the noble gases. But recently I've discovered that actually several people predicted the noble gases. Julius Thomson in Denmark, who published this very interesting periodic system that Niels Bohr adopted a little later, made this prediction, that there should be some new elements having weights 4, 20, 36, 84, and so on. These are the current atomic weights of those noble gases. A remarkable error, or a remarkably small error, right? Of course, it's not all that remarkable, because this is being done by interpolation. You know, if you drew smooth curves, it's not all that difficult. But to have the thought of predicting these elements. And he's not even the only one who did this. Lecoq de Bois-Bergrand in France, and an American chemist also predicted the noble gases. Moving on historically, and I am going to finally take a little drink here. By the way, how am I doing with time? Am I... 10 minutes? I started late. What? 15. No, I'm supposed to have 50 minutes, if you look on your program. No, it's not my fault if everyone goes on for too long. You as the chairman should extend my time. Or is the banquet... Okay, all right. I came a long way. And you have no idea how difficult it was to get my visa. I'm sorry. If I told you the story of my visa, it would take even longer. So maybe... Several discoveries were made in physics, which, of course, invaded chemistry and the periodic table. This is deliberately provocative language to say invaded. Among the discoveries are these. And then there were some discoveries in atomic structure made by Rutherford, who began to probe the structure of the atom, the Curie's radioactivity, the development of the old quantum theory, first due to Planck, first established by Einstein, the photoelectric effect. Bohr was the first to apply it to the atom, and of course came up with these very early electronic configurations. And so here, physics was providing, for the first time, an explanation of why the periodic table is what it is. And it is, of course, that they have analogous electronic structures. Lithium is 2,1, sodium is 8,2,1, for example, and potassium is 8,8,2,1. So because of those analogous configurations, they should behave as they do in an analogous fashion. Then we had real quantum mechanics as opposed to the old quantum theory, right? Due to the contribution, the realization that the electron behaves as a wave, the uncertainty principle, the Pauli principle, and then, or rather, yes, and then the Schrödinger wave equation. Now quantum mechanics was on a more secure foundation. Now, of course, you have 4 quantum numbers instead of 1, which I showed you in the previous slide on Bohr. And now it becomes possible to explain purely theoretically, on the basis of just the hydrogen atom, why it is that the first shell can contain 2 electrons, the next shell 8, the next shell 18, the next shell 32, and so on. And so the physicists got very bold, and one physicist declared that now physics is capable of eating chemistry with a spoon. And Dirac made his famous statement about all of chemistry is reduced to physics. However, the reduction is not complete. For example, going on what I was just saying, even though the shells consist of 2, 8, 18, and 32, if we add those numbers, then we would predict that the noble gases would be at 2, 10, 28, 60, which of course they're not. They occur at these numbers. The reason is not so complicated, is because the shells do not fill sequentially. They fill diagonally, if you wish, using this thing called the Mendeleev rule, right? Which tells us, for instance, that 4s fills before 3d, and then this and this. Right? At the 100th anniversary of the periodic table, in 1969, the Swedish theoretician Per-Olof Lövdin made this statement or remark: the Mendeleev rule, it is perhaps remarkable that in axiomatic quantum theory, the simple energy rule has not yet been derived from first principles. Right. To eat chemistry with a spoon, the physicists should be able to derive this rule from first principles, says Lövdin. 50 years later, it still has not been derived, although there have been several attempts. Now, in the interest of time, since you're pressing me, I will skip this entire important section, especially for chemical educators. Actually, I'm not going to completely skip it, if you'll bear with me. This is a question of the relative occupation of 4s and 3d. 99% of textbooks, with the exception yours perhaps, claim that 4s orbitals are preferentially occupied, but also preferentially ionized in the first transition series. Okay? In other words, the books are telling you that when it comes to the occupation of orbitals, 4s fills before 3d, but when it comes to the emptying or ionization of orbitals, it's the other way around. This makes no sense logically. You can't have it both ways. Right? If this is true, then this should ionize first. Other books feature these diagrams, which show that for potassium and calcium, 4s lies below 3d, therefore it's logical that that should be preferentially occupied. That's fine. But when you move beyond into scandium and the other transition elements, 3d lies lower in energy than 4s. So that should be occupied next. And guess what? That's what actually happens. There is evidence, there's ample evidence that shows that actually 3d is preferentially occupied. It raises the further question of why not 3d3 for the last 3 electrons. I don't really have time to go into that. But I do want to emphasize that actually 3d fills first. So scandium is in fact this, it is not this. And now the relative ionization is very easily explained. Of course, one of these electrons is preferentially ionized. It was the last to come in. It's the most energetic. It's the least stable. Right? So the truth turns out to be a simpler explanation than the explanation you find in most books, which necessarily needs to be very contorted because there's no choice otherwise. Why not 3d3? Well, because the 4s orbital is less compact than the 3d orbitals, and so electron-electron repulsion can be minimized by putting 2 electrons into here. Okay, a more technical version, I will definitely skip this. Here's the evidence. If you look at Moore's tables of atomic energy levels, these have been known for more than 50 years, you see quite simply that as we build scandium, scandium 3+ has this configuration. Scandium 2+, the spectrum shows unequivocally that 3d electron is the next one to come in. Then 4s1, then 4s2. There's the evidence for what I am saying and what other people have said. So, how does this leave the Madelung rule? Well, it disturbs the Madelung rule because it means the Madelung rule is no longer the rule for the relative order of occupation. It may be true for potassium and calcium, but it's not true for scandium. For scandium, 4s does not fill before 3d. Now, some authors have suggested abandoning the Madelung rule because of this problem. Right? I believe that would be a mistake. Of course, we have to respect the fact that this does not predict the order of occupation. The order of occupation is predicted rather by something called the Redbird Rule, which goes something like this. 3s, 3p, 3d, 4s, right? For things of the kind like scandium, following elements. But if you try and follow the Redbird Rule and build a periodic table on its basis, you have this really rather ugly discontinuity, where you have element number 30 followed by element number 19 and so on. In other words, the Madelung rule still gives us the consistent and usual shape of the periodic table. When it comes to thinking about the periodic table as a whole, the Madelung rule still rules, because it does give us maybe not the order of occupation, but it gives us what's sometimes called the differentiating electron. In other words, the electron, the identity of the electron, if one can speak in such terms, that makes the difference between one element and the next one. Right? So for potassium and calcium, 4s. For scandium onwards, 3d is the electron that makes the difference. So the Madelung rule still stands. The challenge that Lovedeen posed some years ago still stands. And I would claim periodic table is not fully explained by quantum mechanics. Physics has not eaten chemistry with a spoon. Not yet. It may be possible. Who's to say? Is there such a thing as an optimal periodic table? Well, I showed you one candidate a bit earlier. Let me come back to it. If you take the usual periodic table and you do two things, you move helium from there to there, and then you cut off the s block and you put the s block here, you arrive at this. A very elegant form. You have to admit this is much more elegant than this. Of course, whether elegance counts in science is another story, which I won't go into. However, there's something that goes beyond mere elegance. It's this. If you look at the familiar periodic table, you'll see that all the periods repeat in length, with the exception of the first one. People have wondered why it is that you have 8, 8, 18, 18, 32, but only 2. Now look at the left step periodic table, and you'll find that, in a sense, symmetry is restored, at least symmetry in numbers. Right? So this is suggestive of the correctness of this table over this table. Chemists don't like it too much, or at least some chemists don't like it too much, because this is placing helium with some quite reactive elements, namely the alkaline earth metals. Right? Is that acceptable? Well, until recently it was not acceptable, but now it turns out that helium does form some compounds. Recently, by which I mean 2017, this compound was reported, a very simple compound of helium, Helium is therefore no longer the most noble of the noble gases. Nobody's been able to do this with neon, however. Right? So on this table, neon is the top of the noble gases. Admittedly, this happens at a pressure of 113 gigapascals, which is a huge pressure. Geochemically speaking, that's no big deal. Those kind of pressures and even higher pressures are... Now, optimal may not be quite the right word here. Maybe the most fundamental periodic table, looking at elements as in the more abstract sense rather than as simple bodies. But remember, Mendeleev stressed, or maybe I didn't say this, for Mendeleev, the periodic table was primarily a classification of the elements in the more abstract sense, not in the sense of simple bodies. That's why you don't have separate places for graphite and diamond and C60. You have one place. That place is carbon, the element carbon. Similarly, isotopes could be thought of as simple bodies. We don't have separate places for the different isotopes, at least not in the conventional table. So it's perhaps the most philosophical table. And it turns out perhaps it's the table that's most in agreement with physics, given that it had to do with, if I can just go back to it, see, this Mendeleev rule is more consistent with this table, because notice that this n plus L equals 1 is this period, n plus L equals 2 is this period. Each of these values represents one period. That's not the case in the conventional table. Right, I am actually coming to the end quite soon, and I'll probably bring it in before the end of time. How long do I have, just as a challenge?
Yes, you had a 7 minutes.
How long?
7 minutes.
7 or 10? All right, this is a separate question. There's something of a debate these days as to whether group 3 of the periodic table should consist of these 4 elements or these 4 elements. The majority of books, by which I mean about 75%, have it like this, but you'll often see these days this. So students naturally ask, well, which one is correct? Here's a suggestion for how to resolve this question. By the way, it has not yet been resolved on the basis of chemical evidence, or physical evidence, or electronic configurations. There's a lot written about this, and none of those kind of arguments seem to be able to resolve it. So stepping outside of actual data and so on, here's a very simple approach, which I hope might resolve it. If you present, so 2 modest requirements, present the periodic table in a 32-column format, which I would argue is more correct than the familiar 18-column. And secondly, insist that the elements should occur one after the other in order of increasing atomic number. So, if you have lanthanum and actinium in the group 3, you've immediately hit a problem. Because if you look, 70, 71, 57, 72, 73, 102, 103, 89, 104. Right? That doesn't work. Do it the other way, everything's perfectly fine. 69, 70, 71, 72. Right? So I would argue on the basis of this, that this is the more correct group 3 setup. Unfortunately, there are some factors that complicate this issue. For instance, the American Chemical Society insists on publishing this periodic table, which is yet another alternative, in which you still have lanthanum and actinium in this group, and you split up the D block in this rather unusual way of having 1 D block group here, and then 9 D block groups here. This way you can kind of have it both ways. You can still have the numbers increasing in order of Z or Z, but you can still have that. So I've been trying to track down who in the American Chemical Society actually suggested or introduced this table, and it's been rather difficult finding who's responsible for this. I'm currently chairing a working group of IUPAC that's been tasked with making recommendations to IUPAC on this question, in the hope that IUPAC will make some kind of ruling. And I would invite anyone who has views on this to contact me or other members of this working group. And with that, I'd say thank you for listening.
Thank you very much. So now we have time for 2 questions.
You're putting the lanthanides and the actinides in the main body of the table, which actually looks nicer, but you said it's more natural. Can you explain that? Why is that actually better?
Oh, why this is better?
Yeah.
Oh, because look at the numbers. 68, 69, 77.
No, not versus that one.
What?
Versus having them down below, as is conventionally done, and putting them up
Okay,
there.
okay. That's the same as what Mendeleev did when he threw out iron, cobalt, and nickel. Why should some elements be excluded from the table? They all belong together. The periodic system is one periodic system. So the putting of the F block down at the bottom is only being done for convenience, to avoid having a wide periodic table. Because the thinking goes that the textbook, the fonts would have to be smaller to be able to put this on a wall chart or in a textbook. It's only for convenience that we represent it as an 18-column table, not for any other reason. So the 32-column is surely the more integrated version of the periodic table.
Thank you. And Professor Vir.
I very much relate to your statement that there are no scientific revolutions. That is very correct. And in that context, I have a question. For me personally, the act of spark of creativity of the periodic table is the concept of periodicity. And I'm not so sure that Mendeleev was the first one with that concept. And my question is, can you pinpoint who in the history of chemistry first said to the public, hey guys, there must be some periodicity, even if the proposed periodic table was totally wrong? Because I think that's the spark of creativity.
The first person that said it explicitly was de Champcourtois, the Frenchman 7 years before Mendeleev. However, as I try to say, even the discovery of triads is, in a sense, the implicit discovery of periodicity, but not made explicit, not published in any form. So it depends what you mean. And that's my point, is that this is a gradual evolution, not a revolution. Of course, we all like heroes. Like we're here today because it's the 150th anniversary of Mendeleev's table. So it's great to have winners. But actually, I suggest, and other people have agreed, that science is a collective enterprise and it's a gradual enterprise. And I think Thomas Kuhn does a disservice to science by focusing, because if you focus on revolutions, you focus on the heroes, the revolutionaries.
Okay, I think that we can give you the time for the third lab question.
Thank you
Wait.
for your explication. Dmitry Viz, Moscow. I understand your explication very well, and I according with you. I would like to know that beginning of periodic table is accomplishing electron by Niels Bohr principle, horizontal movement, and bottom of periodic table accomplishing of electron formula according to diagonal principle of Mendeleev. It's contradiction on my point of view.
Okay.
Thank you.
Why is it is it because it's upside down or something?
Yes,
Okay.
it's two principles. It's first I begin speak Russian, and after I speak English. You understand me, but it's contradiction.
I'm not clear. Do you understand what he's
It's
saying?
just a different approaches for the periodical laws, you know. And I think it's better to discuss your opinion in regard of your opinion of these periodical systems on the evening today. Okay, it's a better way. And I think that now we need to stop our session because we have